Sensing means literally sensing things from a distance. The human eye, for example, is a natural remote sensor in that it sees or senses from afar. Many kinds of remote sensors have been developed over the years, ranging from telescopes for astronomical studies to a variety of geophysical prospecting equipment that enable us to search for features hidden beneath the surface of the Earth. The photographic camera is perhaps the best known and most widely used remote sensor. For more than half a century, archaeologists have been photographing sites from the air. The advantages of height enable excavations to be recorded in a way that photography from the ground could never match. An aerial photograph allows one to see the relationship of complex features to one another, and often displays patterns that are invisible on the ground. The techniques of aerial photography have advanced considerably from the 1930s, when PLO Guy photographed Megiddo from a fireman's ladder and from a small spherical balloon. Oblique photography from airplanes has added significantly to our understanding of the ancient countryside of Europe and other parts of the world. In the 1970s, vertical photography from balloons of increasingly sophisticated design became customary on excavations in the countries bordering the Mediterranean Sea. Thanks to the efforts of Julian and Eunice Whittlesey and of Will and Ellie Myers. At the Interdisciplinary Center for Remote Sensing at Boston University, archaeologists, geographers, and geologists are making use of the world's most advanced remote sensors to study the Earth's natural and cultural resources. Dr. Farouk El-Baz, former director of the Smithsonian's Center for Earth and Planetary Studies, is the director of the new center.
The exploration of space by NASA has resulted in a very rapid development of remote sensing technology. The sensors used today do not only cover the basic parts of the electromagnetic spectrum that are visible to the human eye, but also ultraviolet, infrared, and radar portions of the spectrum are recorded. These sensors that fly in the space missions record in digital format. So the computer laboratory is now as essential as the photo darkroom. With the aid of computers and image processes, the images recorded by the remote sensors are stored, analyzed, and recreated on computer screens. There we can see and record photographically images that otherwise could not be seen by the human eye. Just to understand how important this is, if you consider the electromagnetic spectrum as the complete circumference of the Earth, the part that is visible to the human eye is only the width of my little finger. This image of Cape Cod that we see on the screen was created from data collected by a sensor known as the thematic mapper. It was carried on Landsat 4. From images like this one, which is a color composite, geologists can, for example, map the structure of the region. Geographers can monitor the environment, and archaeologists can search for cultural resources and evidence of past human activities.
One of the highest priorities of the Center for Remote Sensing is to develop methods of applying remote sensing technology to archaeological research. With the aid of a grant from the W.M. Keck Foundation, the center is developing new tools for research and beginning an educational program aimed at training archaeologists in remote sensing techniques. The first training program was held here at the center in August 1986 and was co-sponsored by the Space Remote Sensing Center located at the National Space Technology Laboratories in Mississippi. An obvious need for archaeological research has been an economical field package that would permit digital recording of archaeological sites at low altitudes, thereby resulting in a resolution, that is, with picture elements or pixels, of 1 or 2 meters or less. Fritz Hemans, Director of Archaeological Applications at the Center, began looking into the problem early in 1986.
With the aid of electrical and optical engineers from Zybion Electronic Systems, we put together a system to create multispectral images over archaeological sites. The video camera is fitted with a sensor known as a charge-coupled device. In front of the charge-coupled device are rotating filters to record in 6 discrete bandwidths of the electromagnetic spectrum, 3 within the region of visible light and 3 in infrared. The rest of the system consists of a portable video cassette recorder, a computer fitted with a frame buffer that allows us to freeze individual frames and digitize them on the spot, a video monitor, and a video transmitter and receiver. In June 1986, a team of archaeologists from the center traveled to Corinth, Greece, to see if the multispectral camera could be successfully flown suspended from a tethered blimp that was filled with hydrogen, and most importantly, to evaluate the system's potential use for discovering and interpreting archaeological remains. Besides myself, the other senior members of the research staff were Will and Ellie Myers, experts in balloon photography, and James Wiseman, who's been conducting archaeological research in the Corinthia for some 25 years.
Corinth was a metropolis not only during Greek times, but also during the period of Roman domination, when it served as the capital of the Roman province of Achaia, and continued to oversee the Pan-Hellenic festival known as the Isthmian Games, held every 2 years at the sanctuary of Poseidon on the Isthmus of Corinth. The American School of Classical Studies at Athens has been conducting excavations in Corinth since 1896, and we are now able to see much of the center of the Roman city, as well as traces of its predecessor. The imposing mountain citadel Acrocorinth that rises at the south edge of the ancient city has been less fully studied, and only one of its 2 seaports, Kenkreia, has been investigated. Lyceum, the city's seaport to the north on the Corinthian Gulf, was reached from the Roman Forum by a broad, paved street. Traces of the harbor works at Lyceum can still be seen. The lines of 2 moles forming the outer harbor extend into the sea, and to the east, the entrance to the inner harbor is preserved. A canal leads through fields to the inner harbor, in the center of which is a base for a long-vanished structure. Archaeological excavations have been conducted only at the southeast edge of the town, where a cemetery, a fountain house, and a few other structures were found, and, not far west of the inner harbor, the largest early Christian basilica ever discovered on the Greek mainland. By flying the multispectral camera over the area, we hope to learn more about the extent and location of the town and the nature of the harbor works. After several days of waiting for calm, ballooning weather, the Myers, aided by the rest of the crew, were finally able to inflate the balloon, not long after dawn.
Everybody let up slowly until I knew.
As the calm continued, the video camera was readied for its maiden voyage on the balloon.
I think we ought to be cautious the first time around.
Let's try walking and see how it follows at 300. How high do you want to go up?
I'd like to go 500 meters.
What?
500 meters.
We'll stop at each.
Start with.
No, we'll stop at each 100 to see what
Yeah.
happens. Ready? I've got it.
We've got to see how stable it is at 100.
You should have a checklist.
It's coming.
It's almost overhead.
Yeah.
We're doing very well.
The wind has died some.
The weather, fortunately, held for nearly 2 hours of continuous filming. Almost all the area we had hoped to cover was now recorded on a video cassette, including some spectacular views of the harbors and the gigantic basilica. After bringing the balloon safely back to the ground, there was time to view the results.
You got a picture?
Yeah.
Is it clear? Distinct?
Yeah. There's the coastline, the shoreline.
So we got maybe 50 meters of it, of the water. I don't think we got a lot of water, though.
Just a little bit.
But,
There.
you know, we
See,
got
now we're getting some more. That is nice. Oh, I can see
That was a
I can
mole.
see the mole.
Okay.
Hey, look at that.
Okay,
Beautiful.
this is when we were going up to 400 meters. With the equipment at the Center for Remote Sensing, we are now analyzing the data from Lekian. The process is similar to analyzing images from satellites. These 4 images show how the same area of the site looks in 4 different regions of the electromagnetic spectrum. At the upper left is the image created from blue light. Upper right, green. Lower left, red. And lower right, infrared. The most dramatic differences are between the infrared and visible light images. For example, vegetation is highly reflective in the infrared because of its chlorophyll content. The differences in reflectance create a characteristic pattern, or what is often called a spectral signature. It can be used to differentiate and identify most natural and man-made objects.
The multispectral camera was flown with equal success over the Roman Forum, over the northern part of the ancient city, and even above Acro-Corinth. Literally thousands of images have been gathered, many of them above areas like Lyceum and Acro-Corinth, for which even conventional aerial photographs were previously not available. The data are now being processed and analyzed in the facilities of the Center for Remote Sensing at Boston University. The field test in Greece, however, has already demonstrated the usefulness of this economic remote sensing system and the feasibility, as well as some of the limitations, of suspending the camera from a tethered blimp. Future applications are already being planned for Greece, for Portugal, and for other parts of the world.